gate classes. So the admission is open for gate 25 and 26. So these are the different courses that are offered by the IIT gate classes. So today we will be looking into GATE 2024 mechanical engineering paper. We will be specifically talking about the section of thermodynamics and its applications. So you can look into here the different type of questions that were asked in the exams and what were the weightage. 1 marks question, it was 2 questions. 2 marks, 3 questions, and total weightage was around 8 marks. So let's go through the questions. So this is the first question. Uh, what is mentioned here is that we have a furnace that can supply heat steadily at 1200 Kelvin at a rate of 24,000 kilojoule per minute. The maximum amount of power that can be produced by using heat supplied by this furnace in an environment of 300 Kelvin. So how do we solve this problem? So basically, if you look at it, what it is saying is that we have a source, okay, and that source is our furnace. So source is the furnace, which is at 1200 Kelvin. And then we have sink, which is our environment, which is maintained at 300 Kelvin. The question what is asked is what is the maximum amount of power that can be obtained. So maximum power that can be obtained, it can be obtained from a source of 1200 Kelvin is by running a reversible heat engine between the source and sink. So let's draw the reversible heat engine. So this is the heat engine. So it receives energy from a high temperature source. Let us say the energy is QH, and it gives the energy to the low temperature sink. Let's say that energy is QL, and it produces a net amount of work. Okay. Since the question is asking about the maximum amount of power, the engine that we are considering here, the cyclic heat engine, this engine is basically a reversible heat engine. Okay. And what is given to us is the heat that is supplied from the furnace is 24,000 kilojoule per minute. So we know the efficiency of the reversible heat engine, which is nothing but the net work produced by the reversible heat engine upon the heat or the energy that is applied to the engine. So this is the definition of basically the efficiency which is valid for reversible and irreversible cycle. And since we are talking about the reversible cycle, so this efficiency is 1 minus the ratio of the temperature, that is the temperature of the sink divided by the temperature of the source. So work is something which we want to calculate, and this is a reversible work because this is maximum work that can be obtained. Okay. The low temperature sink is at 300 Kelvin. High temperature source is at 1200 Kelvin. Okay. The heat that is supplied is 24,000 kilojoule per minute. If you calculate, this factor will come out as 0.75. So you can multiply this with 0.75. The value of energy that is given by the source is given, the unit is kilojoule per minute. Okay, but the answer that are given, they are in kilowatt. So we have to convert this kilojoule per minute into kilowatt. So divided by 60. So you can calculate this. So let's do the calculation here. 24,000 into 0.75 divided by 60. The answer comes out to be 300 kilowatt. So answer is A here. So that's the first question. simple, straightforward application of efficiency relation. And then, since it is a reversible heat engine, application of the formula for the efficiency of reversible heat engine. Using that, we get the answer. Let's move to the next problem. Which one of the following statement regarding a Rankine cycle is false? Okay. Superheating of the steam in the boiler increases the cycle efficiency. Pressure at the turbine outlet depends on condenser temperature. Cycle efficiency increases as condenser pressure decreases, or cycle efficiency increases as boiler pressure decreases. So which one is the false? So I can explain all the things, but I'll just give the answer first. The answer is D here. And let's look at it, why this answer, why we get this as an answer. Okay, so this particular question is related to cycle. What it says, cycle efficiency, it increases as boiler pressure decreases. Let's look into this option, why this answer is false. So now if you look at the Rankine cycle, in the Rankine cycle, what are the components we have? So we have one boiler, we have turbine, we have condenser, and we have a pump. These are the four components which makes the Rankine cycle. The working fluid that is used here is basically the water. Okay, so let's draw the basic cycle. In the boiler, heat is given to the water, okay, and it is converted into steam, okay. Then high temperature, high pressure steam enters the turbine, where this turbine expands and it produces shaft work. Then after expansion, the steam enters the condenser, where in the condenser, basically there can be different type of condenser. I'm just explaining a shell and tube. So there can be tube inside the condenser where cold water may enter and hot water may go outside, and the steam may be flowing on the outer surface. So the high temperature steam comes in. This may be in the basically in the vapor stage or liquid and vapor stage, and finally when entire heat is rejected, the steam is converted into saturated liquid state. That liquid is again pumped by the pump to the boiler. So let's mark the different state. So this is state 1, this is state 2, this is state 3, and this is state 4. And the working fluid, which is basically water, is undergoing a thermodynamic cycle. Now let's look at this thermodynamic cycle on the TS diagram. So we draw the TS diagram. Okay, so we are here. Let us say state 1. Now not state 1, the state 2. That is, steam is entering the turbine. Then the steam expands. Okay, we come to state 3. Then there is heat rejection in the condenser. We reach to state 4, which is saturated liquid state. And then basically from 4 to 1 is basically the pump is coming into the picture, where there is basically a reversible adiabatic pumping process that is happening here. Okay, so this is the entire cycle. 1 to 2 is basically heat addition in the boiler. 2 to 3 is the process where we get turbine work. 3 to 4 is the heat rejection in the condenser, and 4 to 1 is the work done on the pump. Now what we have to do, the option which was false, which we said false, let's try to understand. So this pressure here is the condenser pressure. This is the basically our boiler pressure. Now we will draw the cycle again. In that cycle we will increase the boiler pressure. So let's say the new cycle is this. this is the new cycle. So this is 1 dash, this is 2 dash, and this is 3 dash. Okay. Now what happens when we compare the original cycle with the new cycle? What are the differences that we see? So in thermodynamics, when we talk about the concept of mean temperature of heat addition. Okay, mean temperature of heat addition. That's an important concept. Mean temperature of heat addition. Okay. So if you look at the process 1 to 2, so this is the process 1 to 2, which is marked here, and the process 1 dash 2 dash. And let's say the concept of mean temperature of heat addition is this. Let me tell. Okay. So this is the TS diagram. This is, let us say, process 1. This is 2 till here. So this is the TS diagram. And we know that in TS diagram, for a reversible process, the area under the curve basically gives what? It gives the total heat transfer in that process. And 1 to 2 is a process which is happening inside the boiler. So total reversible heat transfer, Q reversible, will be area under the curve. But in this case, in this process, our temperature is changing. Okay, so what we do is we define a hypothetical process in which temperature remains to be constant. So let us say I defined a hypothetical process, which is this process. Okay, where the temperature is constant, T mean. Okay, such that the area under the curve 1 to 2 and the area under the curve A to B is same. So if areas are same, then reversible heat transfers will be same. So I can write it as T mean S2 minus S1. So this T mean is called as the mean temperature of heat addition. Now efficiency of the cycle or the Rankine cycle can be written as 1 minus T naught by T mean, where T mean is the temperature of heat rejection, T naught is the temperature of heat rejection, and T mean is the temperature of heat addition. So as T mean increases, your efficiency of cycle increases. Now, if you look at the process 1 to 2, okay, where the boiler pressure is, let us say, PB1. We call it as PB1. And that is 1 to 2. And second, you look at the process 1 dash to 2 dash, let us say, where the boiler pressure is PB2. Okay. So you will notice that for 1 to 2 dash, if we calculate T mean, that T mean will be higher as compared to 1 to 2 process. Okay, so this is T mean for 1 dash 2 dash process. This will be higher for 1 to 2. So if 1 dash 2 dash is higher, having higher T mean, that means it is having higher efficiency. So as we increase the boiler pressure, our mean temperature of heat addition is increasing, our efficiency of the Rankine cycle is increasing. But let's look at now what is the option that it is saying. Cycle efficiency increases as boiler pressure decreases. This is false. Why? Because cycle efficiency increases as boiler pressure increases. Okay, so this is the option here, and this is the explanation for that. Hope you have understood. The concept here is basically the concept of mean temperature of heat addition. So as we increase the boiler pressure, our mean temperature of heat addition is increasing. And if mean temperature of heat addition is increasing, that means the cycle efficiency is going up. Okay, let's move to the next problem. Okay, let's look at this problem. So what it says consider an air standard Brayton cycle with an adiabatic compressor and turbine, okay, and regenerator. So these are the components which are given in the diagram. Air enters the compressor. Let's mark basically the different things which are given here to us. Okay, air is entering the compressor at a pressure. What is the pressure? Pressure is 100 kPa and temperature T1 is 300 Kelvin. Okay, and at the exit, pressure is how much? 600 kPa, and temperature is 550 Kelvin. Then what is given? Air enters the combustion chamber at 1250 Kelvin. This temperature is 1250 Kelvin. Then it exits the turbine at a pressure of, let us say, P5, 100 kPa, and temperature T5 is 800 Kelvin. The exhaust air from this turbine is basically used to reheat the air which is coming inside from the compressor. Okay. And it is exiting. So T6 is given as 600 Kelvin. Okay. What is being asked to us? We have to find the cycle efficiency. So let's define. So this is basically a heat engine. If you look at it, how do we define the efficiency of the cycle? So efficiency is basically net work output, okay, W net divided by the total heat that is being supplied. Okay. If I look at W net, where W net is the net work done by the control volume. So turbine will do net work, which is positive. Okay. In case of compressor, we have to supply work. So this will be minus WC, and QC is the heat which is supplied here. Okay. So let's look at it. How do we find out the WT first? So WT is nothing but we have to apply steady flow energy equation to the turbine. Turbine can be considered to be completely insulated here. So turbine work will be nothing but it will be m dot H4 minus H5 by the application of steady flow energy equation. And this becomes m dot Cp T4 minus T5. If we have to calculate WC, again, you can apply steady flow energy equation. It will be m dot H2 minus H1, which is nothing but m dot Cp T2 minus T. What is the heat supplied? So heat is basically supplied in the combustion chamber. That is nothing but m dot H4 minus H3, which is nothing but m dot Cp T4 minus T3. So if you want to calculate the efficiency will be ratio of this, which is T4 minus T5 minus T2 minus T1 upon T4 minus T3. So we need to find out these temperatures in order to compute the efficiency. Let's see what is known to us in this equation. T4 is known to us. Okay. T2 is also known to us. T1 is also known to us. Do we know T4? Yeah, T4 is also. T3 is the only thing which is not known to us. Okay. How do we find out T3? We will apply steady flow energy equation for the regenerator. So in the regenerator, what is happening? The compressed air which is coming in, it is getting heated. How it is getting heated? It is getting heated by the turbine exhaust. So turbine exhaust is at a higher temperature. It is coming in at 800 Kelvin, and compressor, from the compressor to the regenerator, that air that is coming is at 550 Kelvin. So we are utilizing this high temperature exhaust of the turbine to heat the air which is coming out of the compressor. Okay. So if you apply the steady flow energy equation, what do you get? You get the heat which is given by this air, which is the exhaust air which is going out, is equal to the heat which is taken up by the air which is going from the compressor. That will be nothing but it will be, so what is the heat gain by the air which is coming from the compressor? It will be m dot H3 minus H2. And what is the heat lost by the exhaust of the turbine? It will be m dot H5 minus H6. This will be m dot Cp T3 minus T2, This will be m dot Cp T5 minus T6. So you have T3 minus T2 equal to T5 minus T6. So let's substitute here. T3 is something which we want to evaluate. What is T5? T5 is 800 Kelvin, T6 is 600, and T2 is 550. What do we get here? We get 750 Kelvin. Okay. Now we know all the temperatures. So let's look at it and substitute here. So we will put the value. What is T4? We'll just go back and look at the value. T4 is 1250 for us. It's 1250 Kelvin. Okay. T5 is 800 Kelvin. T6 is basically 600 Kelvin. Okay. How much is T3? T3 is 750 Kelvin. Efficiency, let's look at the relation that we got here. It is T4 minus T5, T4 minus T5 minus T2 minus T1 upon T4 minus T3. Let's substitute this relation. 1250 minus 800 minus how much is T2? Let's look at T2. T2 is 550, T1 is 300. 550 minus 300 is how much? Is 1250 and T3 is 750. Let's substitute and calculate now. What is the answer that we get here? 1250 minus 800, 550 minus 300 divided by 1250 minus 750. So this is zero point 0.4. So in terms of percentage, if you want to calculate, efficiency will be 40%. Okay. So this is 40%. Okay. Simple application, simple thermodynamic principles that is there. Let's move to the next problem. Yeah. So here what is shown is a piston cylinder arrangement is shown in the figure. Okay. Has two stopped. So look at it. What is there? He's talking about this stop one. A piston cylinder arrangement shown in the figure has a stop located at 2 meters above the base. The cylinder contains air. So it is containing air at 140 Kelvin and 350 degrees. The piston is resting in equilibrium at a position which is 1 mm above the stop. The system is now cooled to ambient of 25 degree. Consider air to be an ideal gas with R value, the absolute value of the specific work done in the process. How do we calculate it? So we utilize few things here. Let's draw the system first. The concept, important concept in the thermodynamics. What is the system? So first we draw the system boundary. Okay. So I am drawing right now what is the system boundary that I have. So this is my system boundary. Okay. And this air is my system, which I am drawing right now. Okay. So this is my system. What is my system? This is air, which is my system right now. So let's write out what is the state 1. At state 1, what are the thermodynamic properties of this system? The pressure P1 is 140 kPa. Okay. Temperature T1 is 350 degrees. Okay. This is what we know right now. Okay. Okay. Now what is happening is that then it is getting cooled. Okay. So if we draw the free body diagram of the piston right now, let us say if you draw the free body diagram of the piston at this state, let's say on the top you have atmospheric pressure which is acting. Okay. Into area, this gives the force on the top face of the piston. Then we have weight of the piston. On the bottom side, we have the pressure of the gas and the area of the piston. So piston right now in state 1 is in equilibrium position. So if we apply the Newton's second law, basically says summation of forces mass time acceleration, piston is at rest. So what do we get? We get the pressure of the gas is nothing but P atmospheric plus weight of the piston, which is mass of the piston times G divided by area of the piston. Now, when you cool the air, so what happens? In that case, once you cool the air, the piston is going to, the gas basically is going to contract, okay, and the piston will start moving in the downward direction. But during this downward movement, what is happening? Atmospheric pressure on the top of the piston is not changing because exposed outer surface is exposed to the atmosphere, so that pressure is not going to change, that is constant. Weight of the piston is not going to change, it is constant. So the pressure inside the gas is also not going to change during the constant pressure cooling from, sorry, let us say from this position x1 to x2. Okay. After piston comes to the position x2, then the volume of the piston is, or the volume of the system is not changing. Okay. If volume of the system is not changing, and if you want to calculate the displacement work, which is integral of 1 to 2 pdv, okay, that will be 0. So the only work done that is in this process will be the constant pressure process when the piston moves from position x1 to x2. Okay. And how do we, and that is a constant pressure because I told you why it is a constant pressure, because on the top of the piston, atmospheric pressure doesn't change, weight of the piston doesn't change. So inside pressure of the gas also doesn't change. So it's a constant pressure compression process basically. If I say why compression, because the volume of the gas or the air is changing during this compression process when the piston is moving in this direction. So this work done w1 to 2 will be p times v2 minus v1. Okay, this I can write it as, how do I get this relation? Work is integral 1 to 2 pdv in a quasi equilibrium process. So pressure is constant. Integral dv v1 to v2, I get this relation. Okay. Now I take v1 constant, so I get p v1 v2 by v1 minus 1. This is an air. I can consider air as an ideal gas. I can use the ideal gas relation, which is pv equal to mrt. Okay. So p v1 is mr T1. Okay. So the work done will become M R T1 volume. If I want to find out what is the volume here total, okay, let us say time being we neglect the stops here. Okay. Time being you neglect the volume of the stops. Okay. So it will be basically a cylinder where I can write it is like a area of the piston times in v2 what happens, v2 is the position when the piston is going to reach the stop. Okay, so it will be 2 and v1 will be area of the piston times 3. I will just explain this again. So imagine now this is the piston at this position, so this is the piston position at this point. Okay, so if you want to calculate the volume of the system, the volume you can say is nothing but area of the piston times the total height. So initially height is 3, which is V1. And finally, when we do a constant pressure cooling process, height will become 2. So that is why it is 2 by 3. AP can get cancelled. He's asking us specific work. What is specific work? That is work done per unit mass. So we'll take mass this side. R is given how much? It is 0.287. Temperature is 350 degrees C. Initial temperature. Let us convert into Kelvin scale. That will be 623. 2 by 3 minus 1. So if we do the calculation, we get minus 59.6 kilojoule per kg. Why minus? Because it is a compression process. In the compression process, the work is done on the system. Okay. So, but he is asking us absolute value. So absolute value will be 59.6 kilojoule per kg. So hope you would have understood. Simple application of constant pressure, PDV work relation, and then using the ideal gas relation. Okay, let's move to the next problem. Yeah. So in this problem, what is given to us? We have a heat pump. So basically, we have a heat pump. This heat pump is driven by a heat engine. Okay, heat engine extract 150 kilojoule of heat from source at 1000 Kelvin. Heat pump absorbs the heat from an ambient which is 280 Kelvin and delivers it to a room which is at 300 Kelvin. Consider the combined cycle to be ideal. This is important. Combined cycle to be ideal. Calculate the total amount of heat delivered to the room by the heat engine and the heat pump. Okay. So now let us say like this. So the heat which is taken by the heat engine, we will take from a 1000 Kelvin source. Let me designate it as QH. Heat rejected to the room, we say it is QL. Similarly, heat extracted from the heat from a low temperature source, let us say it is Q1, and rejected to the room, let us say it is Q2. Okay. So since the entire system, combined system is ideal, when we say ideal, what does the ideal means? That means the system is free from all the irreversibilities. Okay. It's an ideal system. There are no irreversibilities present in the system. So all the processes which heat engine, the fluid, working fluid of the heat engine, all the processes that it is going is all reversible. So this is a reversible heat engine. Heat pump is also a reversible heat pump. Okay. So let's start. So first we write the efficiency relation for a reversible heat engine. Okay. General relation which is applicable to both reversible and irreversible is what it is. And let us say this work is W. Okay, so this will be net work produced by the heat engine upon heat supplied QH. This is a general relation applicable to reversible and irreversible. But when you use the efficiency relation in terms of the temperature, then it's particularly applicable only for the reversible cycle. So this will become T. Let us call this as TH. This is TL, and I can call it as T1. So this will be TL by TH. Okay. So W we will calculate from here. QH is 150 kilojoule. Okay. TL is 300. That is the low temperature sinks. TH is a high temperature source which is at 1000 Kelvin. So we can calculate what is the work done by the heat engine. So it will be 105 kilojoule. Okay. Now let's calculate how much heat is rejected by the heat engine. Okay. So if we take this heat engine as a system, if I take this as a system, okay. So let's apply first law of thermodynamics for the heat engine. Okay. So what is the relation here? So first I will write here the first law. dq is dE plus dW. This is the general relation. That is, heat transfer to the system is equals to change in energy of the system plus work done by the system. Now we will apply it to a cycle. So once you have to apply it to the cycle, you just do a cyclic integral here, integral relation. Okay. The cyclic integral relation, it will finally convert into what? It will be the summation of net heat coming inside the system. Now, change in energy of the for a cycle. So what happens in a cycle? The working fluid is undergoing a cycle. So it start from state one, go to state two, move to state three, then go to state four, let us say, and come back to state one. So if you calculate the cyclic change, we are starting from state one and coming back to the state one again. So this becomes zero, and this is net work done by the system. Okay. So using this relation, what we get? We get QH. QL is going outside, so that's why minus sign, and this will be W. So we can calculate what is QL, which is QH minus W, which is 150 minus 105, which is 45 kilojoule. Let's now go to the heat pump. So we'll calculate what is the COP of heat pump. COP is desired effect upon work input. What is the desired effect in heat pump? Is that we want to maintain the room at a higher temperature. So desired effect is Q2 by work input, which is W. Okay. And since we are writing now COP for a reversible engine, okay, or a reversible heat pump, this will become TL upon TL minus T1. Because for a reversible heat pump, okay, so the COP relation is basically in terms of the temperature of the of the space that you want to maintain at a higher temperature, and the sink source temperature. It is this relation that is there for the reversible heat. Okay. So if we apply this now, Q2 is something which we want to calculate. W is known to us, which is 150. TL is how much? TL is 300. Again, TL is 300 and T1 is 280. So this will be 15. So Q2, if we calculate, we get Q2 as 150 into 15. Sorry, just one mistake I have done here. This is not 150. The work is 105. So this is 105 into 15. Let's calculate this. 105 into 15. This is 171575 kilojoule. Question is asking us to calculate the net heat delivered to the room. So we have to add both of them. 1575 plus 45. Add 45 to this, you get 1620 kilojoule. So this is 1620 kilojoule. Yeah. So this is the answer. Simple uh, problem. Application of first law. Definitions of a reversible heat engine. Efficiency relation for the reversible heat engine. COP for heat pump. Reversible COP for heat pump. Application of those concepts. Okay. Simple questions. Answer is 61620. I think we have covered all the problems. So in case you need more information for gate classes, you can contact on the below number and the information mentioned here. Thank you. Thanks for your time.